I'm going to give you one announcement. So for the people that want to take dinner today with the group of Cosmology group, they're going to join at 8:30 at Quetzal restaurant. Is that true? Yeah, the main restaurant. So if you want to join all the groups, so please come. So we are going to continue with the lecture with Raphael. So you have to give your second lecture. Thank you.
Okay. Thanks. So in the first lecture, we saw why there was an expectation that there should be a cosmic microwave background, and we talked a little bit about how the spectrum is generated, what the possible distortions are. Today I'll talk about the anisotropies in the CMB, and I'll begin with the kinematic dipole. Since there was a question about it already in the discussion, I'll say a little bit more about it than I would have otherwise. And then I'll start talking about the primary CMB anisotropies. The goals will be in the next two lectures: A, to understand how to compute them, and B, how to actually measure them. To calculate them, we'll have to look again a little bit at general relativity, perturbations around FRW, and then we'll start the calculation of the angular power spectra. So let's first talk about the dipole. So as we discussed, that there's this cosmic microwave background. If you have a thermal bath, then it provides a reference frame. So there's a natural set of observers with respect to whom this is isotropic, this radiation. And it's unlikely that we're at rest with respect to the radiation. We're likely moving. The solar system is moving. We also know that the satellite, in any case, is moving. So one question that's natural is to ask, how would a thermal bath of photons look to an observer in a frame that's moving with respect to the cosmic microwave background? And a relatively straightforward way to derive it is to note that if you have a black body at temperature T0, then the occupation number for each polarization state is just given by this. This is just the usual Bose-Einstein distribution with a zero chemical potential. And the occupation number is left invariant by boosts, simply because you're not creating or destroying particles by boosting. You're just assigning, different observers just assign different momenta to these particles. And so this is a Lorentz invariant quantity, and we find that the occupation number that the observer at rest assigns to the momentum p has to be the same as the occupation number the moving observer assigns to the state with momentum p lambda, where p lambda is just the momentum that he assigns to this momentum here. Or equivalently, by just relabeling things, you find that the occupation number that the moving observer sees for the label lambda p is the same as the occupation number that the observer at rest sees for the boost, the inverse of the boost applied to that momentum. And you can simply work out what the corresponding energy is using a boost into a frame that's moving with velocity beta, and then you get an expression that looks like this. So this is the occupation number that moving observer associates with this thermal bath. Now, what you can do is you can just define a new effective temperature for this observer, T beta, which looks like this. So it's T0 over gamma. This is the usual Lorentz gamma, which is 1 over the square root of 1 minus beta squared. And then you have this, this kind of modulation. And typically, the motions we're interested in are slow. So the beta is small compared to the speed of light, or small compared to 1. And you can expand it, and then this gives you a dipole. Now, one point maybe to briefly make is that we're not directly observing temperature typically, but we're observing the intensity. And so you can expand the intensity out, and you find that you get this kind of a temperature dipole. At this point, it's not yet relevant, but it will become relevant in a second. So this was understood very early on, and experimentalists attempted to measure this effect. Basically, from the beginning, there were early measurements by Partridge and Wilkinson that placed upper limits. And then the first measurement of the right ascension, so at fixed declination, but the first measurement of the right ascension was by Ned Conklin. And the first measurement of right ascension, declination, and amplitude was by Paul Henry from a balloon. So he built the radiometer, sent up a balloon, did the measurement, collected the data, and as all just one person, and all the values he reports are still consistent with the values we know today. And the interesting or fun fact about it is that this was his PhD thesis. Then there were subsequent measurements at higher significance by Corey and Wilkinson, also from a balloon. And then there was the measurement that I think most people are familiar with already, is the measurement of the dipole anisotropy by George Smoot using a U-2 airplane. And this is the prototype of the DMR that was later flown on Kobe. So this is very nice data, very high significance measurement of the dipole. So the question in the discussion session was, how can we actually tell that this dipole is due to our motion with respect to the cosmic microwave background and is not some intrinsic temperature fluctuation? And so I'll say a few words about that. First of all, you already saw in the beginning that I expanded out the 1 over 1 minus beta dot n. So there are higher order terms. The next one can work out is the kinematic quadrupole. So there's also a quadrupole contribution. And here it's now becoming relevant that we're not measuring the temperature directly, but the intensity, because it has a different frequency dependence. So the quadrupole that you see, the kinematic quadrupole, should have a different frequency dependence. The problem is that this is difficult to measure because of the foreground contaminations on the large scales, and this hasn't really been measured, but all the maps are corrected for it, assuming that this is what is actually happening. In principle, with the experiments that we saw with a Pixie or Prism, there should be pretty good hope of measuring this, but so far there's no actual detection of it. There is another effect, which is not coming from the effect of the monopole or the thermal bath at fixed temperature, but there are effects due to the fluctuations in the cosmic microwave background. So again, the occupation number you can write in this way, where this n hat in this case is just minus the direction the photon is moving in. So if I'm looking in this direction, I'm seeing photons that are moving in the opposite direction. So that's why there's this sign. And then you can again apply a boost to this. We already worked out how this transforms. So now all that's left is to work out how the direction of the photon transforms. And if you go through the exercise, then you'll find that the perturbation to the intensity looks like this. So you have the usual kinematic dipole. Then in the dots, there's the kinematic quadrupole and higher order terms. But then there are these terms which are interesting. So on the one hand, the effect that you have is that you're not really observing the temperature perturbation in the direction you're looking at, in the direction n hat of the observer at rest. But if you're looking in the direction n hat and you're moving in this direction, you're observing the temperature perturbation that's slightly displaced. So actually your perturbations are slightly contracted in this direction. So this is relativistic aberration. And then there's another effect, which is modulation. So in the direction you're moving, the temperature perturbations or the temperature fluctuations are slightly larger than in the direction you're moving away from. And again, well, let's not talk about the frequency dependence, but this effect actually has been measured by Planck. So this is something you can actually do with current experiments, and you can extract the dipole also using its effect on the perturbations, which is quite impressive. So if you work out the numbers, the deflection is very small. It's only a few arc minutes, but it's coherent, so you can actually extract it from the data. Okay, so this is what I wanted to say about the dipole. We can discuss it more if there's questions, but if not, then let's move on to the small-scale perturbations. We know they have to be there because we see structures around us, so people were expecting to find them, and in fact, they were somewhat surprised that it took them so long to find them. But the way they're defined, so we'll also be interested in polarization, is again through the perturbation in the intensity that's being observed. Again, from the expansion, we just get the derivative of the black body spectrum, and then we get the temperature perturbation. But then there's also, if we're sensitive to polarization, which I'm indicating here. So this is the polarization angle that your experiment is observing. Then you find a piece that's modulated with a polarization angle, and you can describe it in terms of the Stokes Q and U parameters. So here I'm assuming the radiation is linearly polarized, but this is a very good approximation, or it's true for the CMB. Now, this is a little bit of an inconvenient quantity maybe to talk about the theory, just because it is somehow mixed up between the description of the photon bath and the state of your detector, and it's sometimes more convenient to disentangle it, to write it in terms of an intensity matrix times the polarization vectors for describing your experiment. And then the temperature perturbation is related to the trace of this matrix, and the Stokes parameters Q and U are the parameterizing the trace-free part of this matrix. These are usually shown as color-coded maps, which I think everyone here has seen. So there's delta T shown here. Obviously, not all of it is a cosmic microwave background in this case. There's a lot of stuff here, which is the galactic plane. And then similarly, Q you can show as a sky map. These sky maps are from the Planck experiment. These are both at 100 gigahertz, but you can, there's maps at the various frequencies. Now, if you're interested in the theory, you cannot really predict the maps themselves, because it really depend on the particular choice or set of initial conditions. What you can predict are the correlations. So you can work out the correlation between temperature in one direction and the temperature in another direction averaged over the sky, or the correlation between the temperature perturbation and the polarization, or between the polarizations as well as the higher endpoint functions. For data analysis and comparison with the theory, it's more convenient to use the multiple coefficients. So for the temperature perturbation, this is a function on the two-sphere, so the natural thing to do is to decompose it in terms of spherical harmonics, or alternatively, so then these are the expansion coefficients, or alternatively to obtain the expansion coefficients by integrating your function on the two-sphere against the spherical harmonics. For the polarization, you almost do the same, except that, as I said, these are really the components of a symmetric two tensor. So you should really decompose them in terms of the eigen sections of the corresponding Laplacian, which in this case are the spin 2 spherical harmonics, and this gives rise to the coefficients AP, LM. Now, usually these are not directly used simply because they don't have nice transformation properties under parity, but you can define coefficients AE, LM, and AB, LM, which do have nice transformation properties under parity. So AE, LM transforms like a gradient would. It's not quite really the right terminology, because this was a spin 2 field, but in any case, this is essentially transforms like a gradient, and the B component transforms like a curl. So this is also all well known since biceps, certainly. Now, the correlations between temperature and polarization and so on are then encoded in the what are called the angular power spectra here. So by rotational invariance, you know that this can only be a function of L and has to be proportional to delta LL prime and delta MM prime. This is true at least if you have a full sky measurement. Otherwise, it gets a little bit more complicated. And for Gaussian fluctuations, we know that the two-point function really includes, or the two-point correlations encode all the relevant information. So the odd endpoint functions all vanish for a Gaussian random field, and the higher even endpoint functions are sums of products of the two-point function. So everything is encoded in terms of these angular power spectra if it's Gaussian. Otherwise, we'll have to add higher order correlations. Now, these, as we will see in the second part of the lecture, can be calculated in any given model. I'll go through the example of lambda CDM just because it's our baseline model, but if you wanted to modify it, it should become clear how you would modify it. And they can also be estimated from the sky map. So if you have your measured delta T you just integrate it against the spherical harmonics and get out the multiple coefficients. So this is something you can do, for example, in HealPix. So there's code that does it. You don't have to actually code it yourself. There's just routines that you can use. And then once you have these multiple coefficients, you can compute the angular power spectra just by squaring these things and summing over m, or averaging over m, really. So it's 1 over 2l plus 1, which is the number of m modes. So you're averaging the ALM absolute value squared over the different m values. Now, this is usually called an estimator. Obviously, you can write down the analogous things for the TE, EE, BB spectra. And this version here assumes that I have a full sky measurement, which in practice I never do. I'll say a little bit more about this in the last lecture, but for now this is some idealized experiment. And the nice thing about it is that it's unbiased, which means that if you have a given model and you draw one realization of the CMB, you get one set of ALMs, then measure the observed CLs that you get for it, then you draw another realization and so on and average all of them. Then the average over these guys will be the power spectrum that you fed in. So this will be your theory power spectrum. But there is variance. So you don't really, in a single measurement, get the theory power spectrum out. You only get it out on average. And the variance that's there is referred to as cosmic variance. So if you take the difference between the observed CL in a given realization minus the theory CL, square it, and then do the ensemble average, you find that it's 2 over 2L plus 1 times the input theory spectrum squared. Okay, so now again, let's look at some of the early measurements of these things. So there was a satellite, a Russian satellite, Relict 1, that took data between 83 and 84. And there's, initially this was written or stated as an upper limit. At some point then, I don't know if it's a coincidence or not, but around the time when Kobe reported their measurement, this was rewritten and it was claimed that there was a measurement. To me, one should keep in mind that it's a single frequency measurement, so it's a little bit dangerous maybe to claim that there was a detection, but certainly this satellite was before all the other satellites and maybe is a zeroth generation, or maybe this is first and then Planck is fourth generation, who knows. But so in any case, this was an early measurement that tried to measure certainly measured the dipole. Not sure if it measured the quadrupole. The measurement that everyone associates with the first measurement of the perturbations in the cosmic microwave background is Kobe. We already saw Kobe for the measurement of the black body spectrum. This is now not the FIRAS instrument, but this is the DMR instrument, where we also saw the prototype on the U2 spacecraft from George Smoot. And then this is the map. In this case, it's a measurement at 3 frequencies. This is some ILC type map of the perturbations. So now I'll just briefly go through the measurements as a function of time. Obviously, I can't really do justice to all the experiments. I just want to give you some representative snapshots at times that I think are interesting. So the first snapshot that I think is interesting is around 97. So here in the black dots, you see the Kobe points. And then you see that around this time, we're also starting to see the first acoustic peak. So some of these experiments, are MAD, TOCO, Saskatoon, and there's certainly an indication of the first acoustic peak. You also see that at that time, I mean, now typically people will talk about inflation and the source of structure formation. At this time, people were considering completely different ways of generating the structure, namely in a causal way after the hot Big Bang, which would have been nice, but it doesn't in practice work. So here, these were the theory predictions. This is the data, and now we know that there actually is a peak. So at the time, the statement was that the data doesn't favor these models, but I think if you take it seriously, it already at that point rules it out. The next interesting snapshot is when it became clear that there really was a first and second peak. This is the Boomerang and Maxima data in 2001. And you also see some systematics that are still, so there's the first peak is somewhat smeared out, and the second one is basically chopped off in the Boomerang data. We can discuss why, but in any case. So this is the next step forward, I think conceptually at least. So this is the measurement by WMAP. Here I'm just randomly picking the WMAP 7 data. I could have picked any earlier ones, but this is 2010 from the WMAP 7-year papers. And then finally, this is the angular power spectrum that we have today from Planck. And you see that it's very impressive out to very small scales, out to 2,500 or so. And of course, now we also have very sensitive measurements from the ground of the polarization, which I'm not showing here, but we'll discuss more in the last lecture. So this is from 2015, and the goal for the next this lecture and the next lecture will just be to explain how you calculate the theory curve and what the physics is behind it, and then in the last lecture tell you how the measurement is actually done, so how you generate the data points. So hopefully you'll have an idea at the end of the lectures what this plot actually, what all the ingredients in this plot are. Okay, so we'll begin by trying to compute the theory predictions, and for that we'll need to look back a little bit more at general relativity. In the first lecture, all I did was look at a homogeneous and isotropic universe. So we had a line element that was minus dt squared plus a squared dx squared, just a flat for flat spatial slices. And then we had a stress tensor that was also isotropic. So we had a energy density, and then pressure was all that was needed to describe the fluid. And the pressure we related to the energy density in terms of some equation of state. So P was W times rho, and that was enough to solve the background equations. Now, if we're interested in the anisotropies, we have to perturb around this universe. And if you look at the most general perturbations around this metric, they will look like this. So you can turn on perturbation to the 0, 0 component of the metric, which I'll call H00. You can turn on a perturbation to H0i and Hij. And similarly, you can perturb the stress tensor, the 0, 0 component, 0i and Ij. And one thing that's worth mentioning is that we're free in general relativity to choose any coordinates that are most convenient to us. And under a coordinate transformation, so under x mu goes to x mu plus some small, something that's supposed to be small in terms of some function, then the perturbations of the metric transform in this way. And you see that you can use this to choose any gauge that you find convenient. So what I'll be using is I'll set epsilon naught so that the 0, 0 component of the metric vanishes, and then I'll set epsilon I to make the H0i component of the metric vanish, and this is referred to as synchronous gauge. This is maybe not necessarily the most intuitive gauge, but I'm using it because I want to tell you a little bit about the equations that are usually solved in the codes, and they use synchronous gauge. So in the synchronous gauge, the metric becomes relatively simple. So the metric, the 0, 0 component and 0i are still unperturbed, and then all you have are perturbations in the Ij part of the metric. And for the perturbation of the stress tensor, the perturbation to the 0, 0 component we'll just call delta rho, so just the perturbation to the energy density. And then here we have a perturbation to the velocity of the fluid times the sum of rho and p. And then here there's a perturbation to the stress tensor from just a perturbation in the pressure, which is isotropic. Then there's anisotropic stress, potentially, and then there's just the part from the metric perturbation. Okay, so these are a lot of formulas, but hopefully it's still okay. So one thing that's convenient is to decompose these perturbations into scalar, vector, and tensor perturbations. So for example, for the velocity, we can write it as a gradient and a curl piece. It's a vector, so you can always write it as a gradient and a curl. And then similarly, you can decompose the metric perturbations as a piece that's proportional to the metric. Then there's a piece that's proportional to di dj. And then there's a piece that's, so this guy is supposed to be transverse. And then we can construct this guy, and then the graviton, or the transverse traceless piece of the metric, which is the tensor perturbation. And similarly, we can decompose the anisotropic stress. Now, you might ask why this is convenient, because for now it seems like we've introduced a bunch more ingredients and we've blown up all the equations. The advantage of this is that rotational variance of the background implies that all these equations don't mix. So you can look at one at a time, which is a simplification. Okay, so one comment one can already make at this point is that if you only have a density perturbation, then the only way to make a vector out of it is really to take the gradient. In particular, you cannot really make a curl out of it. And we saw that the E modes are generated by gradient pieces and the B modes by a curl. So this means that scalar modes only generate TT, TE, and EE, but don't generate BB, while vector modes generate all four of them, and so do the tensor modes. Now, if the vector modes aren't sourced, which is the case in most of the models we consider, so they're sourced if you had, for example, cosmic strings around, but in the standard lambda CDM model, they're not, and in that case, one can see from the equations, I won't show this part, but they rapidly decay, and so they're typically ignored. And in those scenarios, the B mode detection is an indirect measurement of the tensor modes or the gravitational waves. So you can see this directly from the symmetries. Okay, so now the next quest will be to work out the equations for all these objects. And to do it, we first have to know when we should start our calculation, at what temperature we should start it. And it's convenient to start it early enough so we know how to set the initial conditions easily, meaning it should be, the scattering should be rapid enough so things thermalize efficiently, but it shouldn't be so early that other degrees of freedom appear in the plasma. So if I go to high enough energies, I have electron-positron pairs. So that's something that you can do. In principle, you can start evolving from even earlier, but it's inconvenient because it makes the equations more complicated. So it's convenient to start after electrons and positrons annihilate, but early enough so you can still set the initial conditions easily. And so a typical range of temperatures that one is interested in would be something like 10 to the 6 to 10 to the 9 Kelvin to set your initial conditions. Now we can, anyway, yeah, let's leave it at that. Then in lambda CDM, around this time, we know that the universe is filled with photons, electrons, protons, helium, neutrinos, and dark matter, and there's also a cosmological constant. And so the question will be how we write down the equations of motion for all these objects. Now, the electrons and protons elastically scatter very efficiently. So there's scatterings between electrons and protons is always fast compared to the expansion rate. And so we can actually describe them as one baryon fluid. So electrons are not baryons, but in any case, we bunch them together because the energy density is mostly made up by the protons. For the cold dark matter, just because it's relativistic, so this really relies on the cold, but as long as it's cold, there's also the hydrodynamic description is good enough. We can describe it as just dust and perturbations around dust. For the neutrinos and photons, it gets more interesting because the neutrinos free stream, which means they have anisotropic stress, and so you typically describe them using a Boltzmann hierarchy. Typically, you don't have to actually use the Boltzmann hierarchy. You could solve directly the Boltzmann equation, but this is what's typically done in the code. So I'll briefly discuss this as well. And then if we're interested in the polarization of the photons, we'll see that we actually, well, it's clear that we have to keep track of it and also describe the photons using a Boltzmann hierarchy. Just writing down these equations is a bit of a mess. I wanted you to actually see the actual equations, not some simplified version. So it took me a while to try and figure out how to best present it. And this is more of an experiment than anything else. But so what I thought in the end might be a useful way is to first study a very simple toy example and introduce all the various notations, bits and pieces of the notation in this toy example. And then it should be easy to see how this generalizes to the neutrinos and the photons. So the toy example that I want you to think about is just a gas of particles that's nearly thermal. So it's thermal plus small perturbations. So this is the case we're supposed to be interested in. And then there's too many particles to keep track of all the trajectories. So what we'll try to do is describe it in terms of the phase space density. So obviously the phase space density is just the sum over all the particles, and then delta of x minus the position of the rth particle times delta of p minus the position of the momentum of the rth particle. So everywhere, it peaks everywhere when you have a particle and the momentum of a given particle. So this is your phase space density, and then typically we smooth it, but for now we don't have to think about that. So we have a phase space density that looks like this. And what we want to know is what the equation of motion for this object is. Now we know that if we're looking at massless particles, the velocity of the particle is just the speed of light, and then times the direction of the momentum of the particle. So it's just the unit vector in the direction the particle is moving. So this is what the xr by dt is. And then for a free system, we also know that they're just flying along. So the momenta don't change. This means you can derive an equation of motion by you act on this object with d by dt. So that's what I'm doing here. And then you see that it acts on this object, which you can write as inside the sum still, you get a d by dxr, and then dxr by dt. dxr by dt I can replace by p hat of r, and this, because I'm multiplying it by this delta function, I can replace by p hat. And the gradient, I can, if I change the sign, replace it by the derivative acting on this x instead of this one. So this means I get a collisionless Boltzmann equation of this form. I hope this more or less makes sense. So there's just a bunch of slides where I'm trying to introduce these things, and I'm hoping one can actually follow along. So if it's too fast, just complain. But here, really, just I'm acting with d by dt on this object. Okay, now, just like for the photons later, let's assume also in this gas of particles, we'll be interested in the temperature perturbations. And again, these are related to the intensity perturbations in the same way as before. So the perturbations in the intensity are just the derivative of the black body spectrum times the change of the perturbation in the temperature. Let's, for now, assume that we have a very simple detector that just is sensitive to all the frequencies. So then what we're measuring is just the integral of this over all frequencies. In principle, you might include band passes in this discussion, but that's really not relevant here. So let's just integrate over all frequencies. And then this integral, because we know the thermal distribution, can just be done, and you get a 4. This 4 is just because the total intensity goes like t to the 4th, and so delta I goes like 4 delta t cubed, and so delta I over I is 4 delta t over t. This is all this equation is saying, and it suggests that you can define what people call a temperature anisotropy. So really it's the anisotropy in the intensity in this case, but it's still called the temperature anisotropy, which is denoted by the little t. And this is the temperature anisotropy. So you take the perturbation to the phase space distribution and you integrate it over all frequencies or all energies, and then you divide it by this thing. So this is at a given space and time. So everywhere at x you can define this quantity, and it gives you the fractional change in the temperature for the particles at that point with momentum in the p hat direction. So this is what this object is. I hope that still makes sense. So if you want to describe your gas of particles this way, this is a convenient quantity to introduce. Okay, so it's easy to see that the differential equation, the equation of motion, it just inherits from this guy. Nothing here depends on either x or time, unless, of course, we have some time-dependent temperature or something overall, but let's not do that. I mean, let's just assume that we keep the size of the box fixed and just look at these perturbations, and then it just inherits this equation. So this temperature anisotropy satisfies a differential equation that looks like this. Now, this differential equation is translationally invariant, so it's convenient to just look for solutions that are using a Fourier transform. So you can look for a solution that's of this form, so your Fourier transform. And then you see here that the only angular dependence in your differential operator is of the form p hat dot q hat. And so the solutions you can always write in a form where there's some overall dependence on the direction of the wave vector. But this just sets your initial conditions, and then it multiplies a function that only depends on the magnitude of q and q hat dot p hat. So this is the next gadget we're defining, and then it's easy to see if you just act with this differential operator on this object, it satisfies a differential equation that looks like this, which we can still call a Boltzmann equation. Now, this is trivial to integrate, but let's not get distracted by that, yeah? Alpha is just, you have to have some set of initial conditions. So there's just some, it's a linear differential equation, so there will be some amplitude that you're free to adjust, and it can depend on the wave vector. And later in the CMB, this will be some stochastic parameters. You might have a gas, and you have some set of initial conditions, and that set of initial conditions is encoded in this alpha of Q. Okay, so then let's say we now want to compute our temperature anisotropies at the origin and at some time t0. Then the way we've defined everything, so this is again the thing in real space, delta t over t, this was just our definition of the thing, is delta t of at the origin, and then the direction of the photons again is minus at the direction I'm looking in. So this is the quantity I'm interested in if I want to compute temperature perturbations, and if I want to compute the ALMs, which is what we want to do for the CMB, then we're just integrating this against spherical harmonics. And this, at the end of the day, leads to an expression that looks like this, where these guys now are defined by decomposing this object in terms of Legendre polynomials. So this integral is relatively easy to see because this Legendre polynomial you can write as 4 pi over 2L plus 1, and then the sum of a product of two spherical harmonics, one y and one y star, where the arguments are q hat and n hat, and then the n hat integration kills one of them. You're left with this, and you get this object, and then you get the I to the L from, I mean, the sign still flips because one of them is actually because of this minus sign. But does this still make sense to everyone? Because this is the part that I actually wanted people to get out of it, because this is what we'll see in the next parts for the neutrinos and for the photons. So if it's too fast, if you just want to stare at it, or if you have questions, does it make sense? Yeah? Yeah. This is, so what I did initially is I'm not saying that the plasma is translationally invariant, I'm just saying that the differential operator that acts on my temperature anisotropy is translationally invariant because it only involves d by dx. It doesn't have any explicit x dependence. Whenever you have that, it's convenient to look for solutions in Fourier space. That's what I'm saying, so that's why I'm introducing this gadget, which satisfies this equation. And then to measure the temp... Sorry? Yeah, I have a Fourier transform. I'm sorry? Here I'm not yet looking at the origin. So here I'm just Fourier decomposing in terms of x, and then on the next slide, yeah, I'm choosing the temperature anisotropy at the origin later on. So here I'm looking at it at the origin, which means I'm using this expression with x set to 0. That's the question, is it? So I'm using this expression with x set to 0, and then here I have mu is minus q hat dot n hat. So in this case, I have that. So from the minus n hat, I'll use, so I set this to 0, this will be minus n hat, so I have this expression with this set to 0, and then I have minus q hat dot n hat, and then I expand this in Legendre polynomials, this gadget, and write these Legendre polynomials as sums over spherical harmonics to do the integral. and I get this kind of expression with these multiple coefficients. Does that make sense? If people want to stay longer, it's okay. I mean, these equations, I'll show again the generalizations of these equations for photons. So it would be good to follow this part. Okay. I'm not sure. So here you see that the quantity we're interested in, or will be interested in the CMB, is really involving only these coefficients here, delta t sub L. And this suggests that you should really write down an equation directly for these guys. And you can do it. I mean, we know what the differential equation is that this guy satisfies. We can just plug this expansion into this differential equation and derive a differential equation directly for the delta t sub L's. And this, in our toy example, just becomes this differential equation, which is called the Boltzmann hierarchy in this case. Now, in this case, as I said, it's maybe a bit of overkill, but it's useful for our photons. And the same kind of equation, I mean, looks the same, you can define for the polarization anisotropy. So does this make sense? This is the origin, basically, of the Boltzmann hierarchy in this case. And now we try to generalize it in various ways. So if you have interacting particles, the Boltzmann equation still looks like this, but then you have a collision term here. So the collision term just tells you that at some rate, omega, so this is the collision rate, you're scattering particles out of the line of sight. So you're losing them. There's a minus omega times the density. You're just scattering them out of the line of sight. And then there's also a contribution of particles that get scattered into the line of sight. And then typically this function will only depend on delta t0 or delta t2 because of the nature of the cross-section. So if you have some isotropic scattering, you only get something that involves delta t0 because you have an integral over all directions. I mean, there's a chance from every direction to get scattered into the line of sight. So it's an integral over all directions, which gives you the delta t sub 0. Now, if you look at this equation, it's easy to see that there's at least a formal solution. So you can move this over to the other side and then just forget about this guy for a second, solve the homogeneous solution, and then from this extract the solution to the inhomogeneous problem, and the solution looks like this. The first contribution that you can see is that the scattering drives any initial anisotropies to 0 if you wait long enough. So it exponentially suppresses initial anisotropies. And then there's this term, which naively looks inconvenient. I mean, I say it's a formal solution because it involves delta t on both sides. But what's good is that these collision terms only involve the lowest multiples. So in this case here, I'm writing delta t0 and delta t2. And so what you can do is actually solve the Boltzmann hierarchy here for the lowest multiples and then obtain all others from what is called the line of sight integral. Yeah? Yeah? For dark matter.
Do you assume that it's not interacting, or?
For right now, I mean, this is still my equation in the toy model. Once it will be photons, there's actually only temperature anisotropies from photons in here, and then metric perturbations. So as I said, the different components of perturbations don't actually mix. You can write down a similar Boltzmann equation for the dark matter if that's what you want to do. Just describe your gas of dark matter particles in this way. But then you will see if you have a dark matter particle that's really cold, so it's non-relativistic, all the higher multiples in this will be suppressed, and you're left with the hydrodynamic equation. So that's what happens for the dark matter. But in principle, if you want to include interactions there for the dark matter, you can. But if later on, when I talk about the cold dark matter, I will assume it's collisionless. Does that help?
Yeah.
Okay, does this all more or less make sense? It's a lot of symbols and things, I realize, but I wanted to introduce them because I'll use them in the next part. Okay. The next thing we have to do, so for now we've generalized it to an interacting theory. What the next thing we have to do is generalize it to a general space-time. And in this, I mean, this is actually very straightforward because we can define the same phase space density. The one thing you have to be a little bit careful about is whether indices are raised or lowered. So here I'm specifically telling you that the phase space density that has the right properties is the one with the x's indices raised, pi lowered. And then you can find the equations for dx by dt, which we'll need to derive the Boltzmann equation or Vlasov equation, and you can derive the equation for the momentum from the geodesic equation. And then once you plug them back in, so again you just act on this quantity with d by dt, and then you generate two terms on the right, one which is the gradient with respect to x, one which is the gradient with respect to t. The gradient with respect to x has the dx by dt, so it has the p over pi over p0, and then this one has this object. So this is all that there is to it if you want to generalize to a general space-time. And then what you have to do, so this is still, there's no perturbation, so what we then do is define some unperturbed density, phase space density, and then perturbations around it, expand in those and expand in the metric, and so on, and we'll see that. So it's a little bit more tedious, but in principle it's straightforward. And then the scattering always happens at a time scale that's fast compared to the expansion rate of the universe. I mean, the individual scattering processes, so you don't have to modify any cross-sections or anything. They're just the flat space cross-sections. Okay, so this was the warm-up, and so now I'll show you the equations for the photons. So hopefully all this made sense. I mean, I'm happy to explain it again later if it didn't make sense. But so for the photons, you'll recognize the Boltzmann hierarchy. This is just the part of the free streaming photons. And then because we're in a background that's non-trivial, so we're not in flat space, there's a modification to this equation coming from the metric perturbation. So this piece represents the fact that we're not propagating in flat space-time. And the rest of it, or these terms here, describe scattering. So again, there's some photons get scattered out of the line of sight, other photons get scattered into the line of sight. This is the monopole, and then here there is this source function pi, and this describes a Doppler effect. So there's some effect due to the motion of the baryonic plasma. The equation, as I said, for the polarization anisotropy looks the same in flat space, and then there's again effects on the polarization anisotropy from scattering. So again, some of the photons get scattered out of the line of sight, others get scattered into the line of sight. And then there's a number of interesting things that one can really see, I hope, directly from these equations. So first of all, let's look at the effect in pi of delta P0. So there's 1/2 here for the monopole, which means the sign here is still negative, which means there will still be exponential damping from the P0. So in the absence of this guy, the P0 monopole is damped, also all the odd ones are damped, and also the quadrupole is damped. So all the polarization multipoles are damped by or erased by Compton scattering. The polarization is really only sourced by the quadrupole in temperature. And this makes intuitive sense. So imagine you have a hotter region over here, and then some colder region, and you have an electron that sees this quadrupole. There will be unpolarized radiation hitting it from this way, from this place, and from this side, and the polarization will be perpendicular to the scattering plane. So you get a net polarization in this direction from this, but you also have radiation coming from the colder regions, and they will be polarized in the other direction, but because there's different amounts of radiation hitting the electron from the different sides, you end up with a net polarization. So I should have made a little animation or something, but I don't have one. So that was my best attempt, but you can ask me again later if that part didn't make sense. So similarly, you can see that Compton scattering sends, so I already explained to you that it sends all the polarization anisotropies to 0. You also see that that in this part of the equation, it sends the multiples L equals 2 and up to 0. The only one that doesn't get sent to 0, as you can see, because this cancels this contribution, is the monopole. And then the dipole also is not set to 0 at is not sent to 0 at early times, because as we'll see, the velocity potential of the baryons is essentially the same as that of the photons and cancels the one contribution. But otherwise, the higher ones are sent to 0, which means that at early times you get hydrodynamic equations. And for those early times, or in general, you can write the density perturbation in terms of the monopole in this way. The pressure is given in terms of this, and so on. So at early times, the Boltzmann hierarchy reduces to the equations of hydrodynamics. And eventually, in the next lecture, I'll briefly tell you a little bit about how to solve these. And this is typically where the intuition about the acoustic oscillations and so on comes from. So this is the part one can see for the photons. For the neutrinos, the hierarchy is simple because there's no scattering, so you just have the free part. And then you again have modification because they're propagating in a non-trivial background. So there's small metric perturbations that have an effect. For the baryons, as I said, they exchange energy and, so for the baryons, as I said, we can use a hydrodynamic description. And so we can write down the conservation of energy becomes this equation. Momentum conservation becomes this. And here's what I mentioned earlier. So at early times, rho gamma over rho b we know is large. And so this term is very large, and it drives these two, the sum here to 0. And this is the velocity potential for the photons. So the baryons and the photons are locked at early times. The dark matter, again, can be described, a cold dark matter can be described in this way hydrodynamically because it's non-relativistic. So if you had something that's relativistic, this wouldn't work. You would have to treat it more like the neutrinos. And again, if you had scattering, you would want to include it here. And then there's the scalar and metric perturbations from the GR equations. So I hope this gives you an idea what the equations are that are being solved. And so what remains is to figure out a choice of initial conditions for this set of equations. So as I said, that early times the Boltzmann hierarchy for the photons reduces to the equations of hydrodynamics. And for those, and all the other equations also have this hydrodynamic form. So there's the dark matter has this form, the baryons have this form. So it's natural to look for a solution where all these perturbations are proportional to each other. So you have delta T0, and all the energy densities are proportional to each other, or the density contrasts, and the velocity potentials are proportional to each other. And these are the initial conditions that are called adiabatic. So you have an overdensity of all the various fluids. And then what makes it easy to solve the system of equations in this limit is that all the modes are outside the horizon, meaning if you compare the scales, so if you looked at the equations, you saw that there was a Hubble rate and there was a momentum. And if you compare the Hubble rate to the momentum, you see the A dependence of H. So H goes like 1 over T, both in the radiation-dominated era and the matter-dominated era. In the radiation-dominated era, A goes like T to the 1/2, so H goes like 1 over A squared. In the matter-dominated era, H goes like 1 over A to the 3/2, but it redshifts faster than the momentum in both the radiation-dominated era and the matter-dominated era. And so if we're looking at a mode that we're observing today deep inside the horizon, if you go backwards in time, it was outside the horizon. So it's k over a or q over a was much less than the Hubble rate at this time. In this limit, the system of equations becomes very simple, and there's one solution where this thing becomes a constant. So this is so that part. So if you make this ansatz and solve the equations far outside the horizon, then this quantity, that's a plus h delta u, where you can really plug any of the delta u's because they're all proportional to each other, this becomes a constant. And in particular, we can call this constant R0 sub q. Then you can solve the system of equations in terms of k over ah, and you get solutions that look like this. So these are the initial conditions that are used in the camp, class, codes, etc. So this gives you an idea what the equations are that are being solved and what the initial conditions are. If you want to modify initial conditions, if you want to add isocurvature modes, you have to modify these initial conditions. If you want to modify, let's say, the dark matter sector, as was asked earlier, you can add interactions to the equations of motion describing the dark matter. You can introduce interactions for the neutrinos, for example, which would mean you modify the hierarchy of the neutrinos, so you would add collision terms over here. So, and these equations, in principle, I can give you a translation to the various variables in the codes, are really the things that are being solved. So this is all you have to modify. So then once you've solved all this stuff, you just compute the temperature anisotropies in the way we discussed it in our free plasma, or you can compute directly the angular power spectra. And here I'm just showing you the two most popular codes. If there's other codes that people use. 5 minutes? All right. Okay, so briefly just a discussion of the... So far, these initial conditions, we started our equations of motion at a temperature between below 10 to the 9 Kelvin. So these are not really what would get theorists too excited, because this is very low energy. This is some EV or KEV physics, which we know all about. But the exciting thing is that we can actually learn something from them about inflation. And that's what I'll try to explain in the last 5 minutes. So if you look at the way the angular power spectra look, so this was the delta sub L. I'm just writing it out in a little bit more detail. There's a spherical Bessel function in there. But then you see that there is a part that is given by the late time evolution, and then there's a part that's set by the initial conditions. So this was the R sub Q that I just told you about. But these are initial conditions naively at below 10 to the 9 Kelvin. So what makes it interesting is that we experimentally see that only the adiabatic solution seems excited, or at least the isocurvature contributions are very small. And this means if the R is really a constant here, it makes it very easy to extract backwards. It's just R is the same all the way back. You can certainly extract backwards all the way until electrons and positrons appear in the plasma. Now, it might, in principle, might happen that the equations change dramatically then, and R is no longer constant, but one can show that R is constant essentially for very general matter content. And this means we can extrapolate even further back. So we're not limited by when new degrees of freedom appear. Even in this more complicated plasma, R will be the same constant. So you can go backwards. One of the things that's a little bit unpleasant now is that we have these super horizon perturbations, and we want to eventually generate them causally. So we don't want to just input some acausal initial conditions. We want to generate them causally. And for this, they cannot have been outside the horizon very early on when we generate them, which means that we want a phase where k over a grows more rapidly than h, or where d by dt of q over ah is negative. And one of the things that does this is inflation. It's not the only thing, but it's the most commonly studied one. And in this case, the picture looks like this, that you generate the primordial fluctuations deep inside the horizon. They get stretched outside the horizon, freeze out. You can compute what the value of R is, and then nothing, not reheating, nothing really modifies it, and you essentially can use the R that you compute here as the initial conditions for your system of equations at temperatures below 10 to the 9 Kelvin. So there's two cases, at least, where we know that this is an attractor. One is a single field inflation. The other one is if you have a phase of thermal equilibrium without any conserved charges. And so in single field inflation, then the anisotropy in the CMB tells us directly about the inflationary dynamics. So this is, in this sense, the initial conditions really tell us something about the very early universe. And I'll leave it at that, and then in the next lecture I'll try to give you a little bit more intuition about what's going on in the plasma, say a little bit more about the acoustic oscillations, and then tell you how you actually measure the angular power spectra, so we complete the ingredients that go into the plot. So.
Thanks. We have time for a couple of questions, very quick questions. Many questions. Is there any?
Hello.
Yeah.
Thank you for your explanation of what happens with the kinematic dipole. Is there any evidence at all that the frame, the rest frame of the CMB, is at rest with respect to the Hubble frame in which the matter moves?
It's certainly consistent with it. I mean, you can see it from the equation. I mean, in these equations, there's no discrepancy. I don't know how strong the bounds are on it. I haven't thought about that very much. But all the calculations assume that that's the case, and it's certainly consistent with all the data we have. But it's something one could check. There should be constraints on it.
There are, of course, several papers that claim that it's not consistent. That there is evidence that that there is a relative motion between the two. Are you familiar with those papers?
You mean relative motion between what and what? I mean, there's the
between
baryons moving relative to the dark matter initially?
Between the Hubble frame and the CMB frame, so that you cannot, in principle, subtract the dipole completely as being due to the relative motion of the Hubble frame with respect to the CMB frame.
Well, I'm not sure why. I mean, really, this dipole, the way I described it, is really just a kinematic effect. And then there's the dipole and the quadrupole, and the quadrupole has a very different frequency dependence from the dipole. You can extract it in principle with PRISM and PIXI in the form of a Y distortion. This hasn't really been done, but I don't see why it couldn't be done. The measurement that I showed, the effects on the perturbations, is not at high significance. So it's the statistical error bars, it's about 4 sigma, including the systematic error bars. It's maybe something like 2 sigma, so it's not a high significance measurement at this point, but it's certainly consistent with the idea that this is a kinematic dipole. I don't think it's inconsistent with it, but.
Thank you.
Any other question? No. So let's thanks again to the speaker, please.